Hello everyone, this is Matthew Wood, and in this report I'll be discussing my results from Lab 3 beam vibration. This report will be a thorough overview of everything from the setup to the results to the conclusions from this lab. The objectives of this lab are to compare the static and dynamic data for a beam, as well as observing the viscoelastic effects that things like tape might have on a beam, as well as seeing how frequency modes might impact beam vibration. To do this experiment is set up very similar to Lab 2 in that there is a DAC microcontroller that's attached to a strain gauge that is attached to a Wheatstone bridge, and for this we have a vertical tape measure to manually measure the displacement at the tip to give some known data, and this shows the Wheatstone bridge setup. For static measurements, data from Lab 2 is used from beam tip position to beam tip load. That's used to calculate the beam sensitivity to tell us how accurate our strain gauge is to give the most accurate results. Similarly, the beam stiffness takes the load divided by the measured displacement, and the slope of that tells us the average stiffness. Both of these are linear relationships. So for the first case, the beam is displaced by 20 millimeters and then let go to freely vibrate. We see that unlike a spring, the beam has a sharp drop and does not fully recover. And since this is a beam and it's not a spring, we don't expect it to fully recover, and things like damping and gravity will play a role in this as well. So to best model it and convert it to a spring equivalent system, some equations are used to evaluate the results as if it was a spring. And we see that the natural frequency, damping ratio, and damp natural frequency can be calculated from this. So as we see from figure 7, there is a clear difference between the actual and theoretical response, since the theoretical response assumes that this is a beam versus the actual response, or the theoretical response is for a spring, the actual response is for a beam. There's obviously going to be a difference, even though the slope during the damping will be about the same. Next, we have the spectrum for this. We see that there's one very high peak, which indicates a natural frequency, and this is a bit larger than the next largest mode, which is about 45. And since there's one very large mode, we assume that this can be the natural frequency, although it is half of the natural frequency we calculated earlier. Next, a quarter was dropped on the end of the beam to create an impulse, and as expected, the beam starts at 0 displacement, has a large jump up to about 15, and then slowly tapers off. So unlike the previous case, there are multiple modes, since the effect of having an object dropped on the beam versus it freely being released will have different effects. So as we see, since there's a large group of fairly large magnitudes from around 200 to 250 hertz, the beam will react differently because of this. The third and fourth cases attach different types of tape to the bottom of the beam to add extra damping. And in the same way as case 1, the beam is pulled 20 millimeters before it's released. As expected, the taped cases have larger damping ratios, since the tape makes the beam more difficult to bend than without the tape. So overall, we see that the tape and impulse increase the damping, and also we see that this table uses the first natural frequency from the spectrum graphs instead of the natural frequency calculated earlier from the equivalent And so in conclusion, the beams will display underdamped responses since it is modeled after a spring system. And depending on the design, this may need to be investigated, whether you want the beam to be critically damped or over damped. This might need to be changed. And beams with extra support will have beams without extra support will have higher frequencies, which is expected since the tape makes the beams more difficult to bend. And we also see that even though the actual and theoretical responses may have similar shapes during damping, there are different magnitudes because they generally are modeled after different structures, that being a spring versus a beam. And lastly, we see how the spectrum graphs can affect how the beam vibrates. The impulse spectrum graph has multiple modes that impact the vibration, whereas the case one only has one, which affects how the beam vibrates. Thank you all for listening.